Today we'll go over engineering data analysis, and we'll review the following topics for our midterms: fundamental counting principle, permutation and combination, counting rules of probability, Venn diagram operations, discrete probability distribution, and continuous probability distribution. So let's proceed to the fundamental counting principle. A security code consists of three letters A to Z, followed by two digits 0 to 9. Letters and digits may repeat. How many unique security codes can be formed? So in answering problems like this for the fundamental counting principle, we need to multiply the events that can happen. So for example, we have three letters A to Z, that's 26. So we can expect to multiply 26 three times, as well as two digits 0 to 9, which is 10. So as we can see here, we have three letters, 26 raised to 3, times 10 raised to 2, which represents the digits. So inputting that on your calculator, you get 1,757,600. So for number 2, a university ID has the pattern LNNL, where L is a letter A to Z and N is a digit 0 to 9. If letters cannot repeat but digits can, how many possible IDs exist? So what you need to do here is have blanks where you will be putting numbers. So for the letters represented by L, the first one we have is going to be 26, since there are 26 letters in the English alphabet. Now for the second one, instead of putting 26, we put only 25 because it stated that letters cannot repeat. So if we pick a letter, for example, we pick A, then for the second letter, we can have any of the letters except A. So that's why we have only 25. So for the digits that can repeat, we simply have 10 times 10. So we get the final answer of 65,000. Number 3. A combination lock uses 5 positions, each set from digits 0 to 9. If the code must not start with 0 and no digit repeats, how many distinct lock codes exist? So for this one, we have the first number having 9 options, since we have 1, 2, 3, 4, 5, 6, 7, 8, 9, but not 0. So for the next one, we have also 9 options, because if this is a non-zero number, then this can be any number from the remaining 9. So for example, we pick here 2. So the digits we can have on the second one are 0, 1, 3, 4, 5, 6, 7, 8, 9, and so on. So if we continue this pattern of no digit repeating, we have times 8, times 7, and times 6. So only 9 options for the first position, and the 10 options are reduced by 1 for every next position. We end up with 27,216 options. The next one. A computer network has 4 servers and 3 routers to be connected in a sequence. If every router must follow a server, pattern SR, 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 S, how many unique sequences can be made if all servers and routers are distinct? So we could write blanks like earlier, or we could simply count how many S's and how many R's there are. So it says here that there are 4 S's and 3 R's. A shorthand way to represent 4 times 3 times 2 times 1 is to simply write it as 4 factorial. Likewise, for 3, we can also write it as 3 factorial. So inputting this on your calculator, we get 144. So for number 5, how many diagonals can be made from a dodecagon? So first, let's tackle the concept of diagonals. A diagonal is something that is drawn between two vertices on a shape. Specifically, it cannot be drawn from a vertex itself and to its neighbors. So for example, we have this pentagon here. We cannot draw a vertex here, and we cannot draw a vertex here or here, but we can draw here. So repeating this for all of the points, we eventually get this. So there are 5 diagonals in this pentagon. So the pattern we need to see now is that this is a dodecagon. It has 12 sides. So we shouldn't assume that there are 12 diagonals. Instead, let's use the fundamental counting principle. So a dodecagon has 12 vertices, and it can draw a diagonal to any vertex except itself and the vertices beside it. From here, we have n for every vertex, and n minus 3. So this is the part in the diagonal formula. Then we divide by 2, because a vertex is the same as vertex BA. So for example, if we draw a vertex in these squares, drawing from A to B is the same as drawing from B to A. To prevent counting twice, we have to include 2 in the denominator. So we have 12 times 12 minus 3, which is 9. 12 times 9 divided by 2 is 54. So let's proceed to permutation and combination. So these are processes or operations you can use to simplify the use of the fundamental counting principle when you are dealing with large numbers. So for example, a robotics team of 10 members wants to assign a president, vice president, and a secretary. How many ways can these positions be filled? So the keyword for permutation is positions. So usually for permutation, you want something that needs an order. So for example, president, vice president, and secretary has a specific order of people. So you can list them using the method we showed earlier. So that is 10 times 9 times 8. So when you're dealing with something like this, we can use instead the permutation. So the permutation is written as NPR, or rather n factorial over n minus r factorial. So you can input it on your calculator as shown. So to have this NPR on your calculator, simply use this. So input 10 shift x, so you get to NPR, and then type 3. So that should give you the same answer, 720. So again, the order matters, and the members are removed from the choices once they have been given a position. So you can also input it in factorial form like this. Next, a password consists of 5 distinct letters chosen from the 26 English letters. How many such passwords are possible? Now, if you've encountered combinations before, you may think that chosen automatically means combination. But for the cases of passwords, the order is still important. So for this one, we have 26P5. So that is going to be this, 7,893,600. Next, a smartphone unlock pattern uses 6 dots chosen from a 3x3 grid without repetition, and order matters. How many possible patterns can be formed? Again, for a smartphone unlock pattern, the order is important. So if you draw something like this and leave the 3 dots here, it's going to be different than making something like this. So technically, you use the same dots, but they are not the same permutation. So on a 3x3 grid, on a 3x3 grid, there are 9 options, and you need to pick 6 of them for a permutation. So we have 9p6. Next, An engineering committee of 5 students must be chosen from 12 applicants. How many possible committees can be formed? Now take note, now you are dealing with committees. So a committee is another name for a team where the members have no specific order. It's not like the one earlier from the president, vice president, and secretary that have a known order. So if you have, for example, A, B, C, that's going to be the same combination as C, A, B. So for this one, we're going to use combination. So we need 12C5. So when we have NCR, it can also be expressed as n factorial over r factorial times n minus r factorial. So note the difference here. With the permutation, it's just n factorial over n minus r factorial. But here, we have an additional r factorial in the denominator to eliminate the swaps. So if you notice earlier with the ABC and the CAB, in permutation, those are distinct, but in combination, those are not. So that is what the r factorial here is for. And to type that on the calculator, we have 12C5, which should give us 792. So for number 10, in how many ways can 7 engineering books be arranged on a shelf if 2 specific books must always be together? So if we draw these lines to represent the books, we have 5 specific books that can be arranged in any way that they want, and 2 specific books that must always be together. So if you count the number of things you can arrange, you actually have 1, 2, 3, 4, 5, and 6. So this one, it's counted as 1 because, again, they must always be together. Now, something to take note of is that when you treat one pair as one item, you have 6 items to arrange, but the pair can swap internally. So for example, you have the books earlier represented by lines. If we have something like AB, it's going to be different than arranging the books like this, BA. So since there are swaps, you have to multiply by 2. By the fundamental counting principle, we have 2 times 6p6, or simply 6 factorial. So that answer will give us 1440. Next, circular permutation. How many distinct ways can 7 keys be arranged around a keyring? So if you're arranging things over a round object, like a table or a ring, you need to have circular permutation. So if permutation earlier had n factorial over n minus r factorial, you don't need the denominator anymore. However, you do need n minus 1 factorial. So the reason this is like this is for the 7 keys to be arranged around the keyring, one of them has to be the basis. So you need to know where is the start of the permutation. Because, for example, the linear permutations earlier, if you have 7 keys just in a line, you have a defined start and end point. But for arranging around a ring, you need to choose one of the keys or the elements to be the starting point, and then the other ones can be arranged freely. So in circular permutation, one option is fixed in place for the others to be placed around it. So that gives us 7 minus 1 is 6, and 6 factorial is equal to 720. Next, circular permutation with elements kept together. After an org event, a committee of 10 people go out for dinner. If they invited 3 guest speakers and asked them to sit together, how many distinct ways can they be arranged around a circular table? So here is a common mistake that some students, me included, make. We start with 10 minus 1 factorial. So this is not correct. Because it says here, 10 people invite 3 guest speakers. So that's a total of 13. So there are 13 people at dinner. In applying the circular permutation, we count the 10 org members as 10 units, and we count the guests as 1 because they sit together. From here, we have 11 units arranged around the circle minus 1 factorial. So we have 10 factorial, but that's not the final answer yet, because the guests can swap places with each other. This is equal to 3p3 or simply 3 factorial, because there are ways on how you can arrange them. For example, guest A, B, C around the circle, A, C, B, B, A, C, B, C, A, C, A, B, and lastly, C, B, A. So again, this is just the normal permutations. That's why we have 3 factorial without the denominator, just 3 factorial. And then the 11 minus 1, this is our circular permutation. So our final answer will be 21,772,800. Next, for number 13, a conference seating plan requires 8 participants, 4 men and 4 women, seated alternately around a round table. How many distinct arrangements are possible? Now, if you have 2 separate groups of people, they're not sitting together, but rather seated alternately. You have to put one of the categories first. So, for example, if you put the 4 men first, we have M, 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 M. So one of them has to be the reference. So that's why for arranging the men first, we have 4 minus 1 factorial. Now, if you're going to arrange the women around them, so W, 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 you do not need the minus 1 for the women because the men, one of the men is already the starting point. So you simply have 4 factorial. So again, when you have circular permutation with partitions, do not apply the negative 1 to the other factorial. So that's going to give us 4 factorial times 3 factorial, or 144. Now let's proceed to the counting rules of probability. So we've already used 2 of them, the rule of multiplication and the rule of division, for counting independent events and for eliminating repeated events, respectively. So the next one is the addition rule. So let's use it with combinations. So number 14. A company wants to form a 5-member project team from 4 designers and 8 engineers. At least 2 designers must be included. How many different teams can be formed? So most people would start with the 2 designers and choose them from 4. And then the remaining 3 team members would come from the 8 engineers, right? However, this is just case 1. It says here that there are at least 2 designers. So the designers could be 2, they could be 3, or they could be 4. That means the engineers could then be 3, 2, and then 1. They're actually all going towards the same answer. So in this scenario, we have to add them. So adding 4C2 times 8C3 with 4C3 times 8C2 plus 4C4 times 8C1, we get 456. Again, there are three ways because there are at least two designers needed. And there are four designers, so we can go from two, three, or four designers. And then we add the other engineers to fit the five-member project. Number 15, subtraction rule. So here, we subtract something from a certainty to find out the opposite of it. So for example, the probability of something not occurring is the probability of it occurring subtracted from 1. So for example, if there is a 20% chance of succeeding, that means the chance of not succeeding is going to be 80%. So let's apply the subtraction rule here. The reason we use it instead of the addition rule is that we need at least one letter, but there are actually five letters. So it's easier to know what happens when we don't have at least one letter. Similarly, for the three digits, we want to know what happens when we have no digits at all. So we use permutation because the order matters. Again, it is a password. Valid passwords before the condition amount to 8p4, since before the condition we have 8 characters to choose from, and you have to choose 4 of them. Now we have to subtract the passwords that are impossible or are invalid. So to have no digits, we would have A, B, C, D, and E. So that's 5 choices, and we choose 4 of them. So that would be 5p4. And then for these ones, for the cases where there are no letters, it's impossible because the digits are only 3 and we need 4 characters. So if we need 4 characters to complete it, we would need a letter. So that's why it's impossible. So this is the thing we have to subtract from here. So 8p4 minus 5p4 is going to equal to 1560. So that's the number of events or the number of valid passwords that are possible for this item. Number 16. 5 types of sensors, A to E, are to be arranged in a line on a circuit board. If sensors A and B must not be adjacent, how many different arrangements are possible? So this is similar to our elements kept together, except this time they must not be adjacent. So the probability of them not being adjacent, or rather, the number of events where they are not adjacent is equal to 1 minus the events or the number of events where they are. So we have the number of possible outcomes being 5 factorial because we have 5 sensors, A, B, C, D, and E. So sensors A and B here cannot be placed together, and they can swap. So they can be B and A. Similar to the number we have answered earlier, A and B are considered as one unit, and then there are 2, 3, 4 units in total that can be arranged. So that's why the possible ones are 5 factorial from the sensors A to E minus 4 factorial from the restricted ones times 2 since A and B can swap. They are the same as B and A. So our final answer is going to be 72. Number 17. A sensor array has 10 modules. 3 will be chosen for calibration. If module M1 must always be included and M2 and M3 cannot be chosen together, how many possible selections are there? So there are 2 conditions that are given. So first is M1 must always be included. and then M2 and M3 cannot be chosen together. So for this one, we will only be applying the subtraction rule on this one, cannot be chosen together. Specifically, this is how we will do it. The number of possible ones is for there to be M1 is always chosen. So that would be 1C1 times 9C1. Since there's only one way to choose one item, it's basically negligible. So we are left with 9 items left, and we need to choose any two of them. Since we need to choose three of them. This is already one of them, and we need to choose two more. So that's why we have 9C2. Likewise, we have this 2C2 for the not allowed events. This because M2 and M3 cannot be chosen together. So the ways they cannot be chosen together are two, because there's two elements, C2, because you choose both of them. So when they cannot be chosen together, the thing you have to subtract is when you choose both of them. So 9C2 minus 2C2 equals 35. So there are 35 possible selections. Machine produces bolts, 95% of which meet quality standards. If 3 bolts are tested, what is the probability that all 3 pass inspection? So when we have the counting rules of probability, it is the number of events over the number of possibilities. So in this case, we are already given the P of E, which is 95%. So you could interpret this as 95 over 100. Or if there's 1000 of the bolts, it would be 950 over 1000, and so on. So when you have this 95%, you could input it in the calculator as 0.95. And then you have to raise it to 3. Since if you're testing 3 bolts, you have to find the percent of 95% times 95% times 95%. So it should give you 85.7375% or 0.857375. Next, probability with subtraction rule. A box has 7 green, 5 yellow, and 3 red LEDs. If one LED is chosen at random, what is the probability it is not yellow? So, to get the things that are not yellow, what we could do is to find 1 minus the possibility of yellow. So there are 5 over 7 plus 5 plus 3, 15. So the possibility of that is going to be 10 over 15, which can be written as 2/3 or 66.6667%. Another way you can do this is to check for the green and the red LEDs. So that's going to be 10 over 15. So it will yield the same answer. Next up, we have conditional probability. So this is used when we assume the first event to be true to determine the probability of the second event. So a bag contains 6 red and 4 blue capacitors. If 2 are selected at random, what is the probability that both are red? So let's have R and B. So we start with 6 red and 4 blue. So this chance is going to be 6 over 10. So if both must be red, then that means that the one we choose will be subtracted from the red ones. So it's only 5 left, and the 4 is unaffected. So we have second chance being 5 over 9. So again, for conditional probability, the condition is that the first one must be true to determine what the second one will be, since this is for both. So that gives us 1/3 or 33.3333%. So now let's proceed to Venn diagram operations. Venn diagrams are diagrams that use intersecting circles to represent the relation between two sets. So for example, if we have class of 40 students, we need to start with a box where we write U is equal to 40 at the bottom. And then we have 25 that like mathematics. So we label one circle as M. 18 that like physics, labeled by P. And then 12 that like both. So usually in these type of problems, we start from the middle. So this will be 12. So this is our starting Venn diagram. If a student is chosen at random, what is the probability that the student likes at least one of the two subjects? So it means that the student can like math or physics. So in logic, when we have this, math or physics, in math, we can have it represented by M union P or MUP. So this is our Venn diagram now. 25 for math minus 12 is equal to 13. So 13 like math only. 18 minus 12 is 6, representing the people that like science, rather physics only. So now we have this part and this part. In order to find this whole part, which is the union, we need to add it to the intersection. So one way to do it is to add 13 plus 12 plus 6 to get 31. Another way to do it is to have M plus P minus their intersection, since M plus P minus their intersection. This effectively prevents the intersection from being counted twice when you intersect the Venn diagram. So we have 25 plus 18 minus 12. So that's also going to lead to 31. Now the question asks, what is the probability that the student likes at least one of the two subjects? We have 31 as the number of possible events, and 40, which is the number of the total number that is possible. So here we use U is equal to 40, since in a class of 40 students, 40 is the number or the total number of the students. So 31 of them like either of the two subjects. So that's why the answer is 31 over 40 or 77.5. The next one, a triple Venn diagram. For this one, we have 30 students. 14 play basketball, 12 play volleyball, 10 play table tennis, 6 play both basketball and volleyball here, 4 play both basketball and table tennis, and 3 play both volleyball and table tennis. So you'll see the drawing I made here. The ones filled with red are the ones with intersections. So we can't just add them all, at least not yet. What we need to do is start from the middle. So here it says 2 play all 3. So the question asks, how many students play exactly one sport? So what we're working towards is this area, and this area, without the intersections. So when we start with 2 that play all 3 sports, we put it in the intersection of B, V, and T. Next, we go to 6 play both basketball and volleyball. So 6 minus 2 is going to be 4. 4 play both basketball and table tennis. So 4 minus 2 is going to be 2. And 3 play both volleyball and table tennis. 3 minus 2 is equal to 1. Again, the reason why we subtract is because those are already included here and we don't want to count them twice. So next we have to find the number of students that play basketball only. So as we can see here, B is equal to 14 and 4 of them are already here, 2 are here, and 2 are here. So that leaves us with 6 people here. We do that for everything else in the Venn diagram until it is complete. So for each basketball only, volleyball only, and table tennis only, subtract the sections of the circle that intersect the other circles. So we are asked how many students play exactly one sport. So exactly one needs us to add 6 plus 5 plus 5, which is 16. What if we have a Venn diagram except we do not have the middle? So we can use the other data to find the middle. So in a factory of 200 workers, 90 have training in robotics, 70 in AI, 60 in data analytics, 40 in both R&A, 30 in both R&D, 20 in both A&D. And something I missed earlier, in a factory of 200 workers. If 60 workers have no training at all, how many workers have all R, A, and D training? So let's represent that. We start with the Venn diagram and the box. We know that U is equal to 60, or rather, U is equal to 200. And the prime, or everything that is not in R, A, or D, is 60. We do not know the middle, so we present it as X. So this is our starting Venn diagram. So next we have to assign the intersection of R, A, and D using X. And then the intersections beside it also need X in them. Now the reason why is, going back to the given, 40 in both R and A is going to be represented by this part. However, we have another part here. So this part in the middle is X. So we need to remove X so that it will be only this one, not including this one. So that's why we have 40 minus X. Similarly, for the others, we have 30 minus X and 20 minus X. Now, when we have that, we can also find the workers with any training. So we know that the workers with no training are 60. So 200 minus 60 is 140. So next, we have to solve for R only, A only, and D only. Take note that R only is not a formal way to write the set operations or the set relations, but for convenience, this is the variable I choose to use. So to solve for R only, A only, and D only, we need to do the same thing as earlier. We have to add this, and this, plus the unknown here, which is equal to all of R. So going back to our given, we have 90 training in robotics. So for here, all of this is going to be equal to 90. And then we don't know what this is, but we do know what these are. So we have 70 plus X, 70 minus X rather, is equal to 90. Plus this unknown area. So we do know that this unknown area is going to be 90 minus 70, which is 20, plus X. So we don't know its exact value yet, but we now have a clue on what it is. So this area is going to be X plus 20. Next, we have the other areas. So doing the same steps, we get X plus 10 and X plus 10 for A only and D only. So now we have to add each section of the Venn diagram equals the total. So we know that all of this all of this is equal to 140. So by adding these three plus everything else inside here, we can equal it to 140. So simplifying this, so adding all of these, we see that there is 1, 2, 3, 4 positive x minus 1, 2, 3x, which is how we get x. And then 20 plus 40 plus 10 plus 30 plus 20 plus 10 is going to equal to 130. Transpose this to the other side and you have x is equal to 10. So now you can see, you can also double check for yourself if you solved it correctly. So if you solved it correctly and the given is correct, you can assume that none of the sections would become negative. Remember that we represented it as the intersection of R, A, and D. So this represents the workers that have all R, A, and D training. So our final answer is 10. Next up, we have discrete probability distribution. So discrete probability distribution is another way to handle the probability when you are combining it with fundamental counting principle techniques. Rather, these become quite long, so I'll show you how to use them. So the first one is hypergeometric distribution. From a batch of 100 circuit boards, 15 are defective. If a shop orders 5 circuit boards, find the probability that exactly one is defective. Okay, so remember how the probability of an event occurring can be represented by n over e. Sorry, number of events over number of possibilities. So basically, what we want to find here is exactly one of those is defective. So defective is the one that we are looking for. It is the number of events. Next, we have the number of possibilities. So they order 5 circuit boards. So that would be our n of number of possible events. You could do this with FCP, but it would be a bit long. So there's a shorter way to do this, which is hypergeometric distribution. First, we need to assign variables n and k. So capital N would be the possible choices. So it says here 100 circuit boards. Lowercase n would be the possible chosen. So how many of 100 did we choose? We chose 5 because we ordered 5 circuit boards. Capital K would be the desirable choices. So since we're looking for the defective ones, the choices that are desirable are the 15 defective ones. Lastly, we have the desirable chosen. So in this scenario, we have exactly one is defective. That's why our K is 1. If we are asked to show the entire probability distribution, K can be anything from 0, 1, 2, 3, 4, or 5. So this is represented by the random variable x sometimes. So you'll see this in our formula later. But what you need to know for now is that we need exactly one that is defective. So we won't be using any of these, at least not yet. We're going to need only one. So this is the formula for hypergeometric distribution. The possibility of k equals x is equal to the combination of uppercase K and K times the combination of n minus k capital and lowercase n minus k over the combination of n and lowercase n. So an easy way to memorize this, if you encounter these a lot, is that x is going to be a random variable. It can be 0, 1, 2, 3, 4, or 5 because out of the 5 circuit boards, there can be 0 to 5 defective circuit boards, yes. But in this example, we have exactly 1. So this is the thing you need to replace with 1. Next, this part here is the number of defective boards. So out of 15, we choose 1 defective board. This one on the right is the number of OK circuit boards. So if 15 of them are defective, that means 85 are OK. So out of the 85 ones, if we choose 5 circuit boards, 1 is defective. That means 4 of them are OK. So that's why we use this here, 85 over, 85C4 for this one. And this one at the bottom, capital N over lowercase n is, capital N choose n is going to be 100 choose 5 or 100C5. It's because out of the 100 circuit boards, we choose 5 of them. So let's erase the ink. Okay, so this is our formula. Now, if you're writing it on paper, you can write it like this. But if you're using a calculator, you can write it using C, like earlier. So 15C1 times 85C4 over 100C5 is going to be 40.3401%. So that's only for exactly 1 defective. So if you choose like 0, 1, 2, 3, 4, 5 for x, then you would get different percentages. If you add all of those up, it should add to 100% because again, we are doing discrete probability distribution. We are distributing the probability of 100% over multiple cases. So another one for hypergeometric distribution, a bag has 6 red, 5 blue, and 4 green marbles. So we know that there are a total of 15 marbles. 3 marbles are drawn without replacement. Find the probability that exactly 2 are red. So it says here that there are 6 red marbles. So our big K is equal to 6. So we have 6C2 times 9C1 over 15C3, following our formula earlier. So again, this comes from 15 minus 6 and 3 minus 2. So doing this should give us an answer of 29.6703%. So you can ignore the one that is typed here on the screen. That's a typo. So the correct answer is 29.6703%. Now what if you wanted to do it a different way without using the hypergeometric distribution, or if you simply prefer the fundamental counting principle? While it's not applicable for all cases, you can do it in some cases for problems like these. So a second method, we can compute the probability of getting the first 2 to be red. So this is going to be red, red, and not red. So if you recognize this from earlier, this will be our conditional probability. So we start with 6 red marbles and 15 total. So that's 6 over 15. So assuming we got 1 red, that 6 minus 1 is now 5. And 15 minus 1 is now 14. So that gives us 5 over 14. Then we have to multiply it again. So you could notice that 14 minus 1 is now going to be 13. Now remember, we are computing for not red. So if there are 4 red marbles left, it means that there are 13 minus 4 not red marbles. So the 13 minus 4 represents the marbles that are either blue or green. So we don't need to know which ones are blue and which ones are green. The important thing is they're not red. So we have 9 not red over 13 total. So multiplying all this gives us 9 over 91. Now take note, this is not our final answer because we calculated for red, red, not red. However, the final answer says at least, sorry, exactly 2 red. So doesn't have necessarily have to be the first two that are red. It can be the last, and the first and the last are red, or the last two are red. So these are cases from earlier. So these are the cases. They are equally likely to happen. So if you have 3 cases, you have to multiply this by 3. So here, let me reiterate the point. The problem says exactly 2 are red, but not the first 2 are red. The total cases are 3. We have RRN, RNR, and NRR. We can simply multiply by 3 since they have an equal chance of happening. So again, ignore this. 27 over 91 is our final answer, which is the same as 29.6703%. Number 26. Binomial probability distribution. A factory packages light bulbs in boxes of 10. Historically, 1 in 10 light bulbs is defective. What is the probability of getting exactly 4 defective bulbs in a box? Now, you might wonder why we are using binomial probability distribution rather than hypergeometric distribution. Well, the answer is because we don't know exactly uh, how many bulbs or how many orders of bulbs we are getting. We just know how many defective bulbs there are in a box, but we don't know how many boxes they actually bought. But we do know that we have 1 over 10. So this is our percentage. It's our probability. So we represent this as P is equal to 1 over 10 or 0.1. This is the probability of something succeeding or succeeding to be defective. So zero point 0.1 is the probability to be defective. Q is simply the probability where it is not defective, where it's working. So 1 minus 0.1 is going to be 0.9. Again, this is for defective and this is for not defective. Next, we assign capital K and lowercase k like earlier. So in boxes of 10, that would be our uppercase K. And 4 defective bulbs in a box would be the lowercase k, because out of 10 bulbs, we are choosing 4. Now let's apply it to the binomial probability distribution formula. So it is the probability of capital K equals lowercase k is equal to k choose lowercase k times p raised to k times q raised to uppercase k minus lowercase k. So let's see what exactly do these letters mean. So this k equals k here basically means we're checking how many are defective. So out of 10, we're checking how many will be defective. So if 4 out of 10 will be defective, that's the probability we will be looking for. Next is the combination. So capital K choose lowercase k is going to be 10C4. So why do we have 10C4? It's because we're choosing how many ways 4 can be defective from a box of 10. Next one, we have p raised to k, which is the probability of the defective bulbs appearing in the box raised to how many defective bulbs are in the box. So this is like our multiplication rule earlier. 0.1 times 0.1 times 0.1 times 0.1, or simply 0.1 raised to 4. Lastly, q raised to k minus k is basically checking the probability that we will get something that is not defective. So if there are 4 defective bulbs in a box, 6 of them will be okay. So that's why we have 0.9, which is the probability of not being defective, raised to 6. So inputting all this on the calculator, we get 1.1160%. So let me verify if it's correct. 10C4 times 0.1 raised to 4 times 0.9 raised to 6. So yes, I can verify the answer is 1.1160%. Now, for our last subtopic, we have continuous probability distribution. The difference between discrete and continuous is that we can count how many there are in discrete. In continuous, we are focusing more on the percentages. So the percentages give us an idea of how many there are, but it doesn't tell us exactly how many there are. So let's proceed with the Poisson distribution. So a website gets an average of 10 orders per day. What is the probability that the website will receive exactly 12 orders tomorrow? So here, we're not choosing anything anymore. It's just telling us that there is an average of 10 and there is a value of 12 we have to compare against 10. So here, we use the Greek letter mu to represent the average, and then we represent 12 using x, so this will be our variable. So the formula for the Poisson distribution is this: e raised to the power of negative mu times mu raised to the power of x all over x factorial. We have e raised to negative 10 times 10 raised to 12 all over 12 factorial, which gives us 9.4780%. So for example, if this is the mean, that is 10, it will have a higher probability if you get exactly 10. If you have 11, it might go down. 12, it might go down a little bit more. 13, 14. So for number 28, a small cafe near a college campus is open from 9 a.m. to 9 p.m. every day. They serve 100 meals in a day and sell thrice as many meals past 5 p.m. compared to earlier hours. What is the probability that they serve 4 meals at any given hour? So first, we'll notice that the given 100 meals in a day is the mu for a day. However, the question is asking at any given hour. So at any given hour, we need to find the mu for the hours. So let's start with 9 a.m. to 9 p.m. And then we also mark 5. So you'll notice that they sell thrice as many meals past 5 p.m. So in this situation, it's near a college campus, so the students are probably eating dinner. So we represent this as 3 mu, since it's thrice as many meals past 5 p.m. compared to earlier hours. Assuming that our average is mu, and it applies from the hours 9 a.m. to 5 p.m., and then it's tripled between 5 p.m. and 9 p.m. We have 8 hours here. So 9, 10, 11, 12, 1, 2, 3, 4, 5. And here we have 4 hours from 5 to 6 p.m., 7, 8, and 9. So we have the equation 8 mu plus 4 times 3 mu is equal to 100. So again, even if there are twice as many meals compared to the average during a certain time period, I think that's still an application of the mean. So solving this, we have 20 mu is equal to 100. And the mu, or the average, is 5. So this is just the ratio. So now that we know that mu is 5, we can identify x to be 4. The Poisson distribution of 4, 5 is equal to e raised to negative 5 times 5 raised to 4 all over 4 factorial, which should give us 17.5467%. For our last item, we have the normal distribution. The mean duration of television commercials on a given network is 75 seconds, with a standard deviation of 20 seconds. Assume that the duration is normally distributed. What is the approximate probability that a commercial will last less than 35 seconds? So for this one, we have the condition last less than 35 seconds. And then this is our probability. So we are solving for this. If you recognize this, then you might be familiar with the bell curve. So what we're going to do here is find a z-value on the bell curve and then solve for this area. So that area is equal to the probability of x being less than 35. So let's identify our variables. The mean duration is 75 seconds. So this can be our mu or our x bar. So x bar is another way to represent the mean. With a standard deviation of 20 seconds. This is denoted with the Greek letter sigma. So first, let's solve for the z-value. So the z-value, for those who don't know, it's a value we can use to search up a corresponding probability on the z-table. So if you have a copy of this, simply solving for the z-value will give you the answer to the problem. So first, to answer what is the z-value in the first place, you need to have x minus x bar over sigma. So x, by the way, is this one. It's our value of 35 seconds. So that's why we have 35 minus 75 and then divide by 20. If you have a z-table with you, you can look for the corresponding probability. So if you don't have a z-table with you or if it's not allowed in your exam, use this formula. So this formula is a variation of the normal distribution formula. Next, what is this? Why do we need this negative infinity to 2? Well, the explanation for that is on the bell curve, we are solving for probability of x is less than 35, right? We found that the corresponding z value for that is negative 2. So on the bell curve, we have this line to represent negative 2. And everything to the left of it is what we are looking for. Now you can do this by integrating from negative infinity to negative 2. However, most calculators, especially the common calculators that we college students are using, cannot integrate from negative infinity to negative 2. So a workaround is we can integrate from negative 2 to 0, which is the halfway point. So a special property of the bell curve or the normal curve is that if you draw a line at exactly the middle, the area of this will be 0.5. So basically, what we're doing is we need to find something that is bounded by two actual numbers we can put in the calculator. So this green part I've put here, that is the integral where we integrate from negative 2 to 0 because again, we can't integrate from positive or negative infinity on our calculator. So if you see this, what you need to do is, again, the probability of the left of z is equal to negative 2 is going to be the red part represented here. Half is going to be 0.5 or the blue part represented here. And then green is going to be the middle part, which we will be using on our calculator. So again, to calculate this, we have the probability that z is less than 0 minus the probability that z is between negative 2 and 0. So what you need to do here is use the same formula from here, except now you have to replace this with 0 and this with -2. Since again, changing where you are integrating also changes what you need to put in the calculator. Now, for this part, the z squared over 2, you should look at your calculator to see what is the variable of integration here. So as you can see, it's dx, but for here, it's dz. So what you need to put here is x itself. So you can do this here. Now, another important thing is if you're using the variable here, it should be x. Do not substitute z integral or else it will be wrong. If you try to put z, well, there's no z on this calculator. But if you try to put any other letter or perhaps the number itself, that z is equal to -2, it will be wrong. Because again, there is already a dx sign here and you are already integrating on these bounds. So next, the lower bound is going to be -2 and the upper bound is going to be 0. So it might take a while to calculate, but it should give you the answer 0.02275013195. So if you are instructed or if you prefer expressing your value as a percentage, simply multiply it by 100. So that is the final answer for the continuous probability distribution. So thank you so much for listening. I hope you enjoyed this video and found it useful in your studies.